why do we need a water analysis at all? What different types of water do we have? And what legal basis or what frameworks do we have for a water analysis? And then we'll show you one example to show how it all the information that has to be included in a water analysis, and we'll have a quick look at the analysis results.
There's always the question, why do we need a water analysis? So we quite often hear we don't need a water analysis, and anyway the effort for a complete analysis is far too high. We always recommend to have a water analysis. You know, tap water isn't tap water, it's always a bit different. So on this slide you can see that in the long term, we always have a downtrend for the costs. So I'll just make an example. So if you don't have water analysis and you design the unit incorrectly, and there are parameters like, for example, activated carbon that would be needed for removing chlorine or anything in your countries mostly, and you forget this, then in the long term you have a higher invest because you need to remove the chlorine. And this is the reason why we invest the like 500 to 1,000 euro for the water analysis in the beginning, and on the long term the cost will decrease.
Exactly, because if you have to implement something later, of course that will be more costly than to do it right away.
Absolutely, yes.
Where do these different water types come from? We have a quick look at the water cycle first. What happens? Pure water evaporates from the surface of the sea. This water gets condensed, and then we get cloud formation, and water reaches land again as precipitation, rain, snow, whatever. If we have seepage, we get new groundwater. We have groundwater formation, or runoff leads to surface water formation. That means rivers, lakes, whatever. This has some influence on the properties of water, of course. So groundwater passes certain rock formations and will contain mainly minerals that are dissolved from these rocks. Surface water will contain particles, for example, sand, clay, and so on, organic material as well. And also, as we go down the reaches of the river, we will have an increasingly higher salt load, so that at the end, just before the river mouth, we will have brackish water. And then we come to seawater, where we have, because of the constant evaporation, a relatively high salt content of approximately 35 grams per liter.
So in this picture, we see the different types of water. So as you know, Herco is always called, we purify pure water. So we are mainly working in the drinking water section, sometimes in the sea and brackish water, and also sometimes in the well water. So as said, our main section is drinking water, tap water.
Legal regulations, what is important for water analysis? One big, let's say, reference point or guideline is this publication from the World Health Organization. So they have guidelines for drinking water quality and also the parameters that have to be tested, but the recommendations that are not legally binding. So still this is used in many countries that don't have their own drinking water law as a point of reference. In the European Union, we have the Drinking Water Directive. We have a new version now that has taken effect in January 2021, and this will have to be implemented into national law within 2 years. This Drinking Water Directive has changed a bit, so it requires more monitoring. There are some newer adapted limit values for certain constituents, and there are stricter hygienic requirements for materials in contact with the water, for example. We also have the local regulations. In our case, in Germany, that's the Drinking Water Regulation, or in German, Trinkwasserverordnung. That's the abbreviation you see there. This is, of course, the implementation of the previous European Union directive, and we will get a new regulation as the new Drinking Water Directive is implemented. In your country, there may be something similar, or maybe you work more with the guidelines of the World Health Organization, but the values in all these guidelines are usually somewhat similar. Okay, and then there are sometimes this regulation refers to technical rules that can be DIN or ISO in Germany. That could be some organization like VDI, which is sort of some German engineers. But again, these rules are, let's say, relatively harmonized, at least inside the European Union.
On this slide, we see an example for a water analysis. So this will be, or is, a typical one that you get from the local water supplier. You have like the microbacteria parameters or organics and things like that. We have the chemical parameters, and also sometimes some washing or cleaning parameters. So this is in German, don't be confused.
Yeah, unfortunately, this is a really nice one. So we didn't have that in English. So we said we'll use it anyway.
Yes. So.
And by the way, there I see this, you have the MESFET, that's the measuring value, right? And then what is the one on the right?
This one.
Yeah.
This is the limit from our drinking water regulation.
Okay, so usually you have that in your analysis so that you can compare directly if you're within the limit values or not.
Furthermore, on the right side, we have always the testing method. So if you want to take a sample of something and you're not sure what testing method the laboratory should use, you can always check in a standard analysis and check for the measuring method.
This is about the analysis results. What is important here? Sampling has to be representative, so you can have a very good analysis, right? On paper, everything looks good. But if the sampling wasn't done well, let's say for drinking water, you have to let the water run for 10 minutes, for example, in order to get really from the main line and not from water that was standing there for a few hours. Or if transport took too long, if the water sample wasn't cooled during this time, it can be that you get results that are simply not representative and not what you will get afterwards during operation. The standardized procedures that Denis talked about just now ensure that the results are comparable if you compare different samples. And you have to think also about limit values, so blank value, detection, and determination limit. Blank value is if you would analyze water without a constituent, what value you would get then. Detection limit is when you can really detect a constituent. And determination limit is when you can quantify it. Detection limit means that really, depending on the method you use, you will always have some sort of limit, and under this limit you cannot detect a value. So if you have a result that says 0, that's technically incorrect. Usually you get results that would say, for example, under 10 micrograms per liter, because that would be the detection limit. The units, as we mentioned just now, usually milligrams per liter. If it's high, could be gram per liter. If it's very low, microgram per liter. Or ppm as the equivalent of milligram per liter, which is, I think, more common in the English-speaking countries.
Yes, absolutely.
And sometimes you will see this is more for waste from the wastewater side, for example, that you get NO3N, so nitrate nitrogen instead of NO3. So sometimes you have to do some recalculations. The same goes for hardness, let's say, German degrees hardness, French degrees hardness.
Yeah, or ppmCA is CO3.
Exactly, but you can find values for this in literature, so we haven't included this because it's a pretty short time and we have a lot of information. Then we'll go to the physical-chemical parameters. We'll have a look at temperature, electrical conductivity, which is very often one of the most important ones, the relationship between electrical conductivity, total dissolved solids, TDS, and resistance, also the pH value, color, turbidity, and the silt density index, and finally gases.
For the temperature significance, it is important for the flux rate and salt rejection of the RO. So what we mean with that is that we design our units to 15 degrees Celsius. If the water gets warmer, you have a higher flux but less salt rejection. And on the other side, if you're going down with the temperature to like 10 degrees, then you have a decreased flux and also, but a better salt rejection. So in general, we can say per degree Celsius, you lose 3% of flux when you're going down, and also on the upper side, the opposite way. So 3% flux rate plus.
So that means 5 degrees can really make a difference already. Absolutely,
yes. So if you go even up to 10 degrees, which is our limit, from 15 degrees down to 5 degrees Celsius, it would be already 30% flux rate that is lost.
And then remember, we did a webinar last year, right, on energy efficiency, where we talked also about the variable frequency drive of the pumps. So this is really helpful if we have conditions that are not standard conditions, right?
Absolutely, yes.
Okay, so if you want, check out that webinar. It's very interesting if the temperature differs.
We always need a reference value for conductivity, bicarbonate buffer systems, and O2 saturation, because it's always on a point, where we need to have temperature and the other value. So typical temperatures for drinking water are 15 degrees Celsius. So not in every country. So in the southern ones, it's much more. It's warmer, the water. The groundwater from medium depth is approximately at 10 degrees Celsius. Dam or lake water can go down to 4 degrees Celsius. Stream water 5 to 25, and seawater from 4 degrees to up over 30 degrees Celsius. Always depends on the sea, of course.
Exactly. So next parameter, electrical conductivity. The conductivity measures the transport of the electric current through ions, of course. If you don't have any ions, you wouldn't have any conductivity. So you indicate the conductivity in microsiemens per centimeter or millisiemens per meter. And it gives you an information about the total concentration of ions. So it's a very general value. It doesn't say anything about which ions you have, but it says something about the amount. It's very common because it's an easy measurement. It's easy to do. It's not costly. It is temperature dependent. So one should always have the indication of the temperature at which the conductivity was measured. Usually it gets normalized to 25 degrees, for example. And we have typical conductivities of, for example, drinking water, 200 to 2000 microsiemens per centimeter, usually more on the lower range. The typical permeate of a single stage reverse osmosis would be under 20 microsiemens per centimeter, very approximately. It, of course, depends on the feed water as well. And a double stage, like our NDP plants, for example, would be under 5 microsiemens per centimeter. If you look at seawater, you see already that's quite a lot higher. That's up to 55,000 microsiemens per centimeter.
Electrical conductivity, total dissolved solids, and resistance. So conductivity and TDS. So TDS means total dissolved solids, and TDS is equal to the electrical conductivity multiplied with a conversion factor. So Birgit already explained this to me in the German one, why there are different factors, but I couldn't remember. So probably you tell us again.
Seriously.
Yes.
Yeah, the thing is, this is more or less a rule of thumb. It's not an exact value. So this conversion factor depends a bit on the ionic strength of the solution. So depending on the total salt concentration, it will be somewhat different. Usually if you get a TDS handheld measurement that says, okay, you can measure TDS, it measures conductivity and converts with this factor. The most common factor to use is 0.5, but it can be in any range between 0.5 and 0.7. If you really need an exact value of the TDS, you have to measure it, and that takes more time. You have to evaporate the water and then measure what's left. But in many, many cases, this rule of thumb is really good enough, and you can work with the conductivity and extrapolate the TDS from there.
The resistance is the reciprocal, I don't know if I pronounce that correctly, value of conductivity. An example would be 10 microsiemens corresponds to 0.1 megohm per centimeter. The resistance can be used instead of the LC and is used in ultra pure water treatment. So, for example, electrodeionization, where we reach small values. So, in this value, we see below here 0.056 to 0.1 microsiemens per centimeter. It's not a really good scale to compare if it is performing good. So, we decided to use the megohms value so we can really scale this down in good steps.
Right, so when you look at the UP plants at the diluate, you will have the resistance or resistivity measurement, right?
Exactly.
pH value measures the acidic or alkaline character of a solution. As you know, it's unitless. It's the negative decadic logarithm. This is only important. We don't need to talk about the math because you need to remember that one step, let's say from 9 to 10, means a 10-fold increase or going down decrease. The pH value or the change of the pH value if you add acid and base is dependent also on the constituents or the buffer systems. In water, usually you have the bicarbonate buffer system. We'll come to that in more detail a bit later. And pH is always measured, 1, because it's really important for the design, and 2, because it's also like conductivity, for example, a fast and inexpensive measurement. We have typical pH values, for example, drinking water pH range that is recommended by WHO or drinking water ordinance is 6.5 to 9.5. Rainwater or mineral water, carbonated mineral water, is a bit more acidic, and seawater is usually a bit alkaline.
the color turbidity or the silt density index. So the color of drinking water often is caused by humic substances or particles, so there's something inside. And it is a typical problem when we are using surface water. So like we see on the right side here, so like rivers or seas and things like this. The limit for the, according to the Trinkwasserverordnung, so the drinking water
regulation or ordinance,
yeah, is 1.0 NTU, and NTU is a really horrible word. It's nephelometric turbidity units.
I think we also heard that for the first time actually in Long when we researched.
Yes, absolutely.
Right?
So we always talked about NTU. Nobody knew what it's meaning. So exactly. So then there's the silt density index, and it's a measurement for the amount of colloidal particles in the water and thus the tendency of the RO to block. So it's a really special measurement that is only for the reverse osmosis systems. We also offered this measurement as a spare part or as an part you can
option,
order.
Yeah, that you can order, right?
Exactly, but usually it's not done on site, so it's already part of the water analysis.
The final part of this physical chemical parameters, gases. Of the gases that can be present who are important, let's say in water usually, this is oxygen and carbon dioxide, CO2. Oxygen has a saturation concentration of approximately 10 milligrams per liter, let's say. It's strongly temperature dependent. If you have groundwater, that's often free of oxygen, depending a bit on the redox potential. If you have water that has been already, that is in a river, that is rainwater, it can be already saturated. For drinking water, it's not so important. There are some limit values, but these have more to do with corrosivity or the corrosion effect of the water. For industrial applications, let's say boilers or whatever, oxygen can be a topic and might have to be removed. This would be also a degassing step, for example.
Yes.
Still, what is more important usually, and I think probably 95% of our degassing applications, or maybe even 98%, is carbon dioxide. Carbon dioxide is part of the bicarbonate buffer system that you see here, but we'll talk about that in more detail in another slide. It is present as a gas at low pH values, and with an increase of the pH, it's converted into ionic compounds, which means hydrogen carbonate or bicarbonate and then carbonate. As a gas, it can pass the membrane just like O2. As an ionic compound, it will be held back and rejected by the membrane. If we have CO2 that passes the membrane as a gas, it will redistribute according to this equilibrium in the permeate and will cause an increase in conductivity. So when we have very strict conductivity values, we really have to look at the options how to remove CO2 either before or after the RO step. Now we'll have a look at the water constituents. We'll look mainly at the salts, really. That's the main focus. After a quick look at the periodic table, we'll have a look at solubilities because that's an important topic too, but really just very, very basics, no chemical calculations. We'll have a look at the main components of the cations, what we find usually in the water, main components of anions. And we'll have a look at this bicarbonate buffer system because that's quite important as well. And we'll just quickly have a look at organics and what effect they have on the engineering, let's say.
Here we see the periodic table. So I think you have changed this already.
Oh, yeah. Yes. This was a bit confusing in the German webinar, so I made it a bit more detailed.
All right. So on the left side, we have the main components of the cations. So the ones I mainly know are natrium, magnesium, kalium, calcium, strontium, barium. I know that those guys make problems.
Oh, yeah, usually in service.
Absolutely. And also here, silica and chlorine. So those are the parts that I know from service that cause the most problems in our reverse osmosis systems.
Exactly. Okay, why some components cause problems and others not is also related to solubility. Solubility basically indicates the extent to which a pure substance, so in this case the ion, can be dissolved in a solvent, in this case water, and this gives you the solubility product. It depends on temperature, pressure, sometimes pH. If the concentration of the components exceeds the solubility product, the substance will precipitate. This is something we don't want in an RO system, of course, because this will lead to scaling. The solubilities are relevant, one, for scaling, like I just said. So if you get scaling, you might have to take down the yields in order not to concentrate the certain constituents so much. It might be necessary to have some pretreatment or to have some anti-scale dosing. But the solubility is also relevant because some salts can only be present in very low concentrations in the feed water or the raw water because they are just not very soluble. An example of this is barium sulfate. This is hardly soluble really in water. Which means the concentration of barium ions that you will get is always or is usually under 1 milligram per liter if sulfate is present, because it will just precipitate out. It can also cause, even with these low concentrations, if there's enough sulfate, scaling at the tail end of the RO. But all these topics about influence on the engineering, we'll just cover that shortly in this webinar, and we'll go into a lot more detail in the next webinars in October and November.
Yes.
As a comparison, you see here sodium sulfate, which is highly soluble. Have a look, this is gram per liter actually. So this is not just 1 to 170, but factor of 1,000 as well. So 1 milligram per liter to 170 grams per liter theoretical solubility. So you see that depending on the solubility, there is a really big difference in the scaling potential of the salt and the concentration of the salt.
I'm not the chemical expert, so I'm trying to understand a bit what is on this slide here, and Birgit will cover it then.
Seriously.
So calcium is one of the most important elements in terms of quantity. Magnesium is also very common found in salt and potash deposits. Strontium occurs in much lower concentration, is neither toxic nor essential to life, no limit value, and barium occurs as carbonate and sulfate, of which barium sulfate is poorly soluble. The limit in our German Trinkwasserverordnung is 1 milligram per liter.
That's right. And we have also included here on the right-hand side some concentrations for you. We won't read all that off, it will take too long. But just to give you an idea of what a typical concentration would be, because we think it's also important to have a look at the water analysis and to say, this looks pretty much average, right? Or to say, this is really a strange value. I mean, if you would get barium, let's say, in a value, usually it's very low, like we said here, less than 100 micrograms per liter even. If you see suddenly 10 milligrams per liter, I would question that value. So it can be useful to have some reference point. These cations are important for hardness. So we look at hardness as well. The total hardness is usually the sum of all these alkaline earth metals that we have discussed in the previous slide. Very often, strontium and barium are neglected because, well, they're so low anyway. And usually that's also, that doesn't make a difference. There are certain groundwaters that might have a higher concentration of strontium, but it's not a very common case. So if you look at calcium and magnesium, that would be the calcium and magnesium hardness. These cations have certain anions to complement them, and mostly they're complemented by bicarbonate or hydrogen carbonate, the correct name. This is the carbonate hardness. So this is a part of the hardness that can be attributed to hydrogen carbonate or bicarbonate. And then the rest is the non-carbonate hardness, which is here the remaining part, NCH, exactly. The non-carbonate hardness is also called permanent because it is retained even when the water is heated, while the carbonate hardness is temporary because it will precipitate as CaCO3, so as lime, and can thereby be removed from the water when you heat it up.
The alkali metals. So only natrium and kalium are relevant in water chemistry. The analysis is time consuming and therefore often not determined. And in rivers, there are only low concentrations, higher values as for chloride associated with seawater. So natrium, as we know, salts, they come from the seawater, like and clay minerals the limit in our Trinkwasserverordnung. Mm-hmm. So by the end of the webinar, you know the German word Trinkwasserverordnung is 200 milligrams per liter, and that's approximately the taste limit for chloride. So where our drinking water actually gets a salty smell or taste, not smell. So potassium, what is potassium? So I don't know this word, so
yeah, well, that's usually, you get that usually from mining, potash mining, that or fertilizer production. In the end, that's for fertilizer usually. Yeah, you probably don't know it because there's no limit value, and usually it's not a very problematic constituent. But both of these are somehow always associated with seawater here. So you will see either there is some rock formation that used to be originally sea, or you have maybe coastal groundwater where you have influence from the sea. And if you have low values, that means usually you're far from the sea, and you will have low chloride values as well.
Okay.
Now we come to the interesting point. Iron and manganese. That is what is much more often a problematic case, as you said.
Yes.
So these occur usually together. Iron is a bit more frequent than manganese. We have some limits, which is iron less than 0.2 milligrams per liter, manganese less than 0.05. I think that's practically the same as in the WHO regulations. Both of them have a water-soluble form and an insoluble form. So the water-soluble one is the reduced form, the divalent form, Fe2 or manganese 2. And the oxidized form is 3 or 4 as an oxidation state, and that one is insoluble. So then it's particulate. That's why it's important to have both values in the analysis. Very often we don't, right?
Yes.
So that's a common problem. It is relevant for the pretreatment because we remove these constituents by oxidation first to get from a water-soluble form to a non-soluble form. And then we separate these particles that form in a filter. Usually oxidation is the rate determining step because it's a lot slower than the filtration. It's strongly influenced by pH and acid capacity, but we'll go into more detail with that topic in the next webinar. That means if we know that this iron or manganese is reduced and water-soluble, we know we'll have to do the oxidation step. So we'll need a lot more time, possibly a larger filter. But if we know this is oxidized, we know that it's already insoluble, and we just have to do the filtration step, basically. So it can be that that makes 50% difference in investment cost for the pretreatment. So that it's really, it really makes sense to have a complete water analysis. When we oxidize it, we have a certain order. Usually iron is fastest and manganese, and ammonia is oxidized with these constituents as well. So that would be the last oxidation step. We had a few projects, I think. Actually, I think Holger had a project just a short time ago where they were also discussing, is it oxidized, is it not? Small filter, large filter. So that's an interesting topic.
Ammonium. I've learned a bit about this in last week, and ammonium is typically present in equilibrium with gaseous ammonia. So it's a component of the nitrogen cycle and associated with wastewater, and the limit value is 0.5 milligram per liter. What I actually learned last week is that it's can be a problem because it can be dissolved and going back after the reverse osmosis into a solid state.
Well, yeah, it can be dissolved and then you get it somewhere where you didn't want it. That's right.
Yes, exactly.
And we had a project where it was, well, the pH was getting a bit higher. Normally, it's not such a big problem because you see that ammonia, you only have a significant percentage of ammonia as a gas when you are over a pH of 8, let's say from 9 on. But in that case, we had water that was relatively alkaline. We passed the membrane. NH3 passed the membrane because it's a gas. And then we had ammonia again in the water where we didn't want it to be after the reverse osmosis. So it's worthwhile to think about it when you have a higher amount of ammonia, that it can be converted to the gas form, and that it will pass the membrane and it could cause you problems later on. So chloride, as we showed you before in the previous slide or 2 slides ago, is also associated, just like sodium and potassium, with seawater in the end. So usually salt deposits, mining, or seawater, groundwater with seawater influence. It increases the chloride concentrations the further you go down in the river, because you will always have chloride, for example, in the wastewater. You have more wastewater influence, you will have more chloride in the river until you reach really brackish water. Sulfate is a bit similar in that it increases along the river flow route. Very often it comes from a geological formation, sometimes also from discharges of wastewater, but very often it can be from rocks like gypsum, anhydrite, whatever. When you have groundwater from a rock formation that includes sulfate, you can have very high concentrations. Like here you see up to 1.35 grams, not milligrams, grams per liter, which would be saturation concentration. So there it really depends a lot on the geology as well.
On this slide, we see my favorite parameter. It's silica on the right side.
Ah, yes.
So this is a really important parameter that gets forgotten very often, and it's really important for the electrodeionization systems, because some of it passes the RO and it really scales or fouls on the EDI stack and blocks it in the long term. And if you know, previously we did, or in the past, they did systems where they recirculated a lot of concentrates and EDI concentrates and put it back in the front in the unit. And this is where they concentrated also these silicates, and they scaled everything on the EDI systems. And they wondered why an EDI system only was working for 3 years. And this is just some basic knowledge that they grew over the years.
True,
yeah.
true.
So carbonate and also fluoride, nitrate, phosphates, silica, which is the one that I met the most in the service side. Bore, not so often, because it's mainly a problem for the microcontrollers, I think.
Yeah, microelectronics,
yes,
exactly.
Microelectronics. But you can also meet it, I think, in power plants sometimes.
That could be that it's a problem there. Yeah. Then we'll go, as we mentioned, we have from the anions also 2 important constituents, and that's hydrogen carbonate or bicarbonate, HCO3 minus, and carbonate, CO3 2 minus. These 2 together with CO2, with carbon dioxide, make up this bicarbonate buffer system or bicarbonate equilibrium, which is the main buffer system in water, also in our cells, really. And the hydrogen carbonate concentration equals basically the acid capacity up to pH 4.3, which is measured by titration. It's also called alkalinity sometimes, or M value. It's important, for example, when you think about pretreatment and how to remove iron and manganese. What is also interesting here, so the ionized parts or constituents are held back by the membrane, are rejected. So it means hydrogen carbonate and carbonate will be removed, but CO2, as we said before, can pass the membrane and will increase the conductivity in the permeate and reduce the pH value as well. CO2 can be removed either by increasing the pH, so we move the equilibrium to the right-hand side. That is a relatively easy option, right, with the dosing pump.
Yes.
Or you can use a membrane degassing stage to remove CO2, which is maybe more invest, but helpful if there's a higher concentration of CO2.
Yes, and you don't have the handling with the chemicals, of course.
That's also true. I think most of the EDI systems we have usually have a membrane degassing stage if it's a problem at all.
Yes, absolutely. Organics, we already have seen some of this before, and this picture we already seen. So the origin of organic molecules can be natural by humic substances or man-made, so by pharmaceuticals, pills and everything, pesticides. And we measure those as BOD, COD, or TOC and DOC, so many words here. So, so what I usually meet is TOC, so the total organic carbon. So that's the most met one. Birgit already told me last week that BOD and COD is more for the wastewater side. Is that correct?
Yeah, I come from the wastewater side. I included it, but I admit that TOC is the more important one.
For dimensioning, it's important to have the organic load because it leads to falling of the membrane. So it can block our membranes in front and layer over, organic surface, and we can't produce anything more. So we need a proper pre-treatment and adapt the dimensioning. And maybe also the membrane type. There are special low-falling membranes that you can install there.
Right, this is something you see in service also a lot, fouling problems.
Yeah.
Now, water analysis in practice. If we ask you for a water analysis, will any analysis do? Is every analysis the same or not? That's what we want to talk about quickly. Then we'll look at assumptions that or what we assume if we don't have an analysis in a project. We'll look at the effects on plant engineering and potential sources of mistakes.
Here on the right side, we see a design program. I don't know which one it is. I think it's hydronautics or something. So
that's right.
As you can see, we don't need all the parameters that you usually meet on a big water analysis. So you see on the cation side, we have calcium, magnesium, natrium, kalium. And also on these values, you already see, okay, quite often we don't even have them or they're not inside. So on the anion side, we have the chloride side. And you see, we have many unnecessary parameters, especially organics. Important parameters are often not included, like silt density index or silica. And we need always an appropriate scope. So for the chemical physical parameters like temperature, pH,
electric conductivity. Sorry.
Yeah, it should be EC or TDS. And they are the most important ions for this design. See right side, not left, and the critical parameters for the RO, which determine the pretreatment, are iron, manganese, silt density index, and so on. So you see they're not included here because we already expect that they are removed with the pretreatment.
Exactly. Yeah, that's important to know. So you can see from this, you already have an idea of what we need, and we have also tried to focus on the ions that are really make a significant input for the design, and to leave out the other ions or organic components and so on that are maybe very important for drinking water analysis because they might be toxic or whatever,
yes, but
that are not relevant for the membrane. Okay, now what happens if we don't get an analysis, which is also, well, often the case, yes. Let's say. We assume usually for the design of our reverse osmosis units that you have TDS of 1000 milligrams per liter, water temperature of 15 degrees, as René mentioned, that you have a silt density index of 3, that means no huge fouling potential or scaling potential rather. That iron and manganese is already removed according to the specifications of drinking water treatment, so under 0.2 or under 0.05. Silica, there I think I have to ask you because you know more about these different limit values. Why are they different?
So mainly because of the EDI. So we are usually with standard ROs without EDI stacks, we are at 25 milligrams per liter. If we go to EDI, they would scale with 25 milligrams per liter. They have lower limits. So in this case, we even use different membrane types. So the UP units with RO plus EDI have special membranes inside that remove more silica. And even with those membranes, we are at a level of below 15 milligrams per liter. Otherwise, they would scale and block our EDI stack. And if you only have the EDI, you need to be below 0.5 milligrams per liter. So that's the limit. So for optimal performance, we need to go even lower to 0.3 milligrams per liter.
So that's quite low already in the inlet.
It is.
Right. Of course, we want free chlorine not to be detectable, and we need a certain inlet pressure. That's mainly for the plant, so that doesn't have too much to do with the analysis. But this is what we assume. you see that with the TDS, we assume a relatively high value that's equivalent to 2000 microsiemens per centimeter conductivity, which means we cover most of the load cases, let's say. Very often drinking water will have a lower TDS, but we want to design our plants in such a way that even if you don't have a drinking water analysis, you're on the safe side that you will cover really most of the waters. Not everybody does that.
Effects on the engineering of the plant. So the electrical conductivity takes effect on the pressure of the RO. So if we have more ions inside, we need more pressure to press them through. We need a bigger pump. We need a different membrane type, maybe. For the temperature, we have already talked about this. So this also has an effect on the pressure of the RO, also on the pump size and everything, and also on the flux of the RO. So the silt density index has effects on scaling. Again, pressure of the RO. If we have scaled ions there, then we need a higher pressure, and the particle separation is required. So for iron, again, we have scaling, which leads to a higher pressure on the reverse osmosis, which means it is blocked later or earlier. Deferrization or anti-scale operation is required for this. The calcium has effect, again, scaling. Calcium can also scale on the membranes, and we need softening or anti-scalant operation. The organics would foul and also block the membrane, so it's a bit different on the sides of the membranes, but all the same effect. So more pressure is needed, system blocks, and we need to clean in most cases.
Okay, so here we show again what pretreatment would be necessary. Again, we will go into more detail in the next webinar or the next two webinars. So if you have a pretreatment with a pre-filtration, possibly also with a flocculation, sand filter or ultrafiltration for surface waters, you protect the membranes against particle clogging because you remove the particles before. You would usually lower the silt density index with this pretreatment. If you have a deferrization or, well, removal of iron really, or removal of manganese, you prevent scaling on the membrane by iron or manganese. If the concentration is low, you could control that still with anti-scale possibly, but that works only until a certain point. So what we really recommend is to remove it. Softening, if you take out calcium, magnesium, also strontium and barium, which clogs scales very easily, you prevent scaling on the membrane, again by removal. Usually softening is used for lower flow rates, let's say less than 10, but this is a really rule of thumb. It depends a bit on if you want to use salt, what you have already on site. But the tendency is for smaller units, you rather use softening. For larger units, you rather use anti-scale operation. In both cases, we have a certain protection against scaling, and that means we can operate our reverse osmosis without any operational problems.
Sources of failure. So this is something that I meet a lot, in after sales, not mainly if you're doing the design, and the main failures can be variations during the year or due to the weather. So if we're taking the river water, sometimes we have more rain, we have more things inside like surface, soft from surfaces, and often the sampling is not correct. So not cooled, during transportation or stored too long. So this is really problems that occur, or used the wrong bottles for the sample. So there are different bottles that you can use for samples, like glass bottles that need to be filled completely, or other bottles. Or also interpreted incorrectly.
So now to recap, we'll come to some examples just to show you from our, let's say, projects or also from other sources, some examples of drinking water or well water, river or lake water, and seawater.
Here we see an example of drinking water. So unfortunately in German again.
It's good for practice.
Yeah, exactly. So here we have the most important one. So in this case, it would be conductivity. Like we have seen before, there are always the limit values, Grenzwert in German, and then we have the values that we actually measured. So the structure is according to a list in the Trinkwasserverordnung, in the German drinking water regulation. And as said before, many parameters are not required for the reverse osmosis dimensioning. So the electrical conductivity is relatively low and corresponds to approximately 400 milligrams per liter. So this is what we see here, 790
exactly.
or something.
So we use this value of 0.5 to convert.
To convert it, exactly. So the devarization or demanganization is already carried out by our public utility companies. So there are no values. I don't see it.
They are very low.
I think it's here, iron.
Yeah,
iron and also manganese. I don't know where manganese is. Here, manganese is here. So really low. They already removed it. So hardness is high. So calcium.
You have it at the bottom, I think, in yellow.
Yeah, it is here. Total hardness at 3.37. And German hardness, it's 18.8 degrees German hardness. So it's quite high. So as you see from the city, we always get hot water and we need to remove calcium and magnesium.
Exactly. Here, for example, you see that silica is not included because for the drinking water, nobody cares about it.
Exactly.
Probably in this case wouldn't be too high, right? In Germany, it's not too high. So if you have an EDI, it would matter anyway.
Yes, exactly.
But for example, if you do a project in a country where you have a lot of volcanic rocks, it can be quite high. So it's not 10 milligrams per liter, it can be 60 or 80 even. So that does make a big difference. What else do we have? This is from a project. This is now, I wanted to say in English, but actually I think it's Serbian. Well, but that happens a lot, that you get analysis from another country and it's a different language, but fortunately you can always see pretty quickly what it is about. This is interesting because this is a negative example, really. This is an analysis of a well water, and the client wanted us to remove iron and manganese. You see that both iron and manganese exceed the limit value, so the limit value is in the center. And these are the results exactly. And the results that are not within the limit values are in gray. So we see that we are over the limit, but we don't know the oxidation stage, which would have been really important for design. We also couldn't get the value. So in the end, we had to design without, and we had to assume that it's all reduced. So we used a large filter. The alkalinity, which is also very important for the design of the filter sizing, was also not determined. We asked the client in the end to send us a second sample with the alkalinity, which we got in the end. And you can see that, the other parameters are not so critical, but this is an example of how it maybe works out in practice, that you have half of the information, and that's not very helpful. So that's why we want to stress really often that the oxidation states are important. It's important to have a full analysis, because in the end, the cost for a full analysis, it's maybe a bit of coordination, maybe 500 euros, let's say, but it's really worth it for the investment or for the total project cost to invest these few hundred euros in the beginning.
Exactly. Here we see the last example with brackish and seawater. So
Oh, well, I'm sorry. I think that was my mistake, actually, because this is the lake water now.
Okay.
This was a project, maybe I just continue. This was a project, also a real project that we did. And this is a lake in Switzerland. And you can see here, we chose in this case just, what was it? The zooplankton. You can see it at the top, which means the small microorganisms that swim in the water. You can see just the variation. So you have a minimum, an average, middle, an average, and a maximum. And you can see already for the different locations or the different types, I think, of animals, so plankton, you can see that there's a big variation. You wouldn't find this, you wouldn't find zooplankton in groundwater anyway, but you wouldn't find this variation. So you see from here from 1.19 to 17 to 61. And this goes for other parameters like particles, like turbidity, a lot of things in river and lake water that you can have big variations, even more in rivers than in lake. So you have a costly pre-treatment very often, possibly ultrafiltration.
Yes.
And for lake water, if you extract water from a very deep location, it usually doesn't matter so much. Because there the variation is low. But if you take water from the surface or from a river, it does matter a lot. So I wanted to show you the variation here. And then we have brackish water or seawater. This is just really a very, very general example, not a real analysis. So this is just to show you, you have a lot more salt concentration. You see here that's approximately 3.5% or 35 grams per liter. And you can have, this is an average example, let's say, but you can have very different salinity, very different salt concentration. So this would be, let's say, North Sea, but in the Baltic Sea, you have only half of that. And if you go to the Red Sea or the Dead Sea, I guess you'd have a lot more.
Yeah.
You have a strongly different temperature also, as we mentioned before. But I think with seawater, you would get, hopefully, water analysis before the project.
Yes.
We would assume.
We would recommend.
Yeah, even though I think we have done projects without, but okay.